This screen looks dark, but by looking through these glasses you can definitely tell it's on. However, tilting the glasses back horizontally and it no longer works. There's no CGI here, so what's going on? Well, the key has to do with polarization and the fact that I snuck an extra polarized lens in front of the camera while you were scrolling a few videos ago. To understand what's going on, I'm going to use this spring to represent light and this foam cut out of sunglasses to visualize polarized lenses. You can think of a polarized filter as having a bunch of slits that let light pass through. In this example, the slits were made vertically to indicate vertical polarization, which is the direction that sunglasses are polarized. Light travels in waves and can travel in any direction. A vertically traveling light wave, so to speak, looks like this. It moves up and down as it travels across the room. While a horizontal one looks like this, it moves side to side. After feeding the spring through my model sunglasses, you can now see that waves traveling vertically can pass through the sunglasses. However, waves traveling horizontally will not make it through and get blocked. So having one lens in front of a light source only blocks out some of the light so that it looks dimmer. But if you place a second lens and rotate it such that it's perpendicular to the first, then at least in theory with perfect lenses, it blocks out all light. The vertical light that can make it through the first lens can't make it through the second one since it's perpendicular, and you can see it here again in slow motion. That all makes some sense, but if you're like me, you might have been surprised to learn that even if you have two perpendicular polarized lenses, you can place a third one in between the two and rotate it at an angle, and light once again makes it through. This clip was from my Two Truths and Trash episode, and spoiler, it absolutely is real. A reason this might be surprising though is because we only did the spring and slits visualization for waves traveling parallel or perpendicular to the slits. However, as mentioned, waves don't just travel in these two directions, but rather can travel at any random angle, like this one for example. Since waves are difficult to see when looking straight at them, I'll just draw a vector with an arrow like this to show the amplitude and direction of these waves. So a vertical one would have a vector like this, a horizontal one would have a vector like this, and if it's at some angle like this one, it would be drawn at whatever angle it's at. It makes sense that a wave traveling parallel to the slits can completely pass through, while a wave traveling perpendicular is completely blocked. But for a wave traveling at some angle in between, you can simply take this vector and separate it into components that are parallel and perpendicular to the slits. Now, as you probably could guess, the component shown in green, which is traveling parallel to the slits, can make it through, while the component shown in red is perpendicular to the slits, meaning it gets blocked. As a result, some does get through, but it's less than if the entire thing was parallel. That's technically all you need to understand why this works, so you might have it already, but it's the best I could do in the length of this short, and you can continue at 234 to see the full walkthrough and a few other cool demos, like trying a bunch of angled lenses to see how much light can make it through.